So hi everyone, welcome to a CSP seminar this week. This week it's our great pleasure to have Mauricio Delbracio from Google Research to give us a talk. Dr. Delbracio is a star research scientist at Google Research. Before that, he's a faculty member at a top public university in Uruguay. And even before that, he did his postdoc with
Guillermo Sapiro.
Yeah, Guillermo Sapiro at the Duke University. And before that, he did his PhD in France. And Mauricio did a lot of interesting work in the intersection of image processing, inverse problems, machine learning, signal processing, etc. And recently, he's a key contributor to the Unblur, a key feature in the Google Pixel camera of image deblurring. And in 2016, he wins the Early Career Prize in some imaging activity group for his contribution to image processing. So today he will talk about some interesting image restoration through inversion by direct iteration. So with that, the room is yours. Welcome.
Thank you. Thanks, Chin, for introduction. I'm very happy to be here. I'm very excited. This is my first time in Michigan, and I arrived yesterday. The weather was much better than today, so I got a little confused. But yeah, so today I'm going to present our work on inversion by direct iteration. That is related to image restoration, but it's even more than that. So, okay, let's get started. What is the idea of image restoration? The goal is to recover a clean, sharp image given a low-quality observation. And there are multiple flavors of this. We may want to get rid of noise, compression artifacts, limited like resolution, or blur, like motion blur, lens blur, right? And the goal is to recover an image that is high quality, but is also compatible to a low-quality observation. And if we take this problem to the extreme, right, where the degradation is significantly, is very severe, right, then this is actually a generative task because we want to generate a new image that is compatible to the low-quality observation. But if there is no signal on the what we are observing, it's just about generating new data. All right, so what is the traditional way of like formulating this problem is as an inverse problem. An inverse problem means that we want to recover a clean, latent, sharp image, given that we know just an observations, right here represented by Y. And in particular, we may know or we may not know the underlying degradation, the model here represented by the operator A, and typically we also observe noise in our measurements. So as an example here, you can see that we can model motion blur by assuming a very simple model that is the convolution with a motion blur term, right? And then we have noise on top. So the traditional classical approach to image restoration was by formulating through a variational energy, right? But a variational formulation where we try to do an optimization problem where we have multiple terms, each of them playing in different contexts. We have, for example, a data fitting term where try to say, look, the image that you're trying to recover should match the model and the observations, right? But we also need to enforce certain regularity on the signal that we want to estimate. And we may also try to model some uncertainty on the operator or on the degradation operator. This has been on for many years, like from the 80s, but even earlier, like in the 50s, there was work on trying to solve tasks like image restoration by Gabor, for example. But lately, what we have been working on, and like many people here, is on trying to combine ideas from data-driven formulations by, for example, incorporating prior knowledge learned from data on the prior terms on this formulation. For example, how to use denoisers as a way for regularizing problems, or other generative strategies like GANs, VAEs, and more recently diffusion, right? Including papers from people that are actually here, right? Those papers, in many cases, they don't do like a variational formulation, but the idea is the same. We are going to use a model-based strategy where we know the degradation and try to leverage prior information into it. This is a very active area of research. So the alternative is to go fully end-to-end, meaning that we are going to use paired data to learn how to do this restoration task. Imagine that you are given thousands of millions of examples, low quality, high quality paired examples, and then we ask the question, can we directly learn a mapping that brings us from the low quality space into the high quality space? Well, the typical way to do this is by training a deep model, right? And then trying to find the parameters that actually minimize some loss functions given the training data. And we can, for example, try to minimize the average pixel reconstruction error. This is probably the simplest thing to do, right? And we can train a model for doing this. So what is the problem? The problem is that inverse problems, imaging inverse problems, are in general ill-posed, meaning that there are many plausible high-resolution images that can lead to a very same low-quality observation, right? So whenever we are going to try to estimate one, what we are going to see is a regression to the mean effect, meaning that we are going to estimate the average of all plausible reconstructions. And this is going to be an image that is blurry. So where is this regression to the mean appear? Well, it's very simple to see in a toy example. Let's assume we have many data points n that actually lead to the very same low quality observation, right? So then if we directly try to find the optimal mapping that minimizes the average reconstruction error, it's very easy to see that it's just like if we minimize the to norm, it's going to be just the arithmetic mean, right, of all the plausible candidates. This is very simple, and we can generalize this to the posterior mean of the posterior distribution. And this is going to be an average of many high-quality images that is going to be blurry.
Well, I have a question.
Yeah.
So that would only be blurry if you're assuming that the average is not like a reasonable image.
Exactly.
Well, like that's typically like.
Yeah, I'm going to show you an example. Yeah, that's a good question, right? In general, this average is going to be out of the distribution.
Okay.
So, and the key thing is like the more ill-posed a problem is, the larger this average, right? So let me show you an example. Here you have like simple case where you have a low resolution image, one plausible reconstruction, high resolution image that if I downsample, I get the low resolution. And here is what you get if you train a model to directly learn this mapping, right? Well, one could say that you see more details, right? I do see more details than in the low resolution image, but you don't see exactly the fine grain and the level of detail that you see on one of the high resolution targets. So this is a typical scenario. So what I'm going to present is InDI, this framework, that we are going to try to avoid this regression to the mean by going through an iterative restoration scheme. And as we will see, this can be seen as an implicit diffusion process where we're just learning this process using paired data, low quality, high quality data points. And it's competitive state of the art on many restoration tasks. And I'm going also to show how this is also a generative framework. So this joint work with Peyman Milanfar, we're both at Google Research. All right, so what is the key idea? The key idea is to split the problem and instead of going directly into the fully degraded to the clean space in one step, we're going to try to do this in multiple steps. How we can split this problem? What we do is the following. We are going to generate these intermediate degradations, right, that are just convex combinations from the high quality image and the low quality input, right, with this parameter T that goes between 1, meaning fully degraded, to 0, which means clean image, right? So the goal is that instead of going directly from X1, the input, to X0 in one step, we're going to try to do this in multiple steps going through this intermediate path of degradations. And the intuition here is that each of these problems is going to be less ill-posed. It's going to be a simpler problem So we are going to minimize this regression to the mean effect by going like little by little. All right, so this is the core idea. But then how do we do this, right? The key part in our formulation is this proposition that actually it looks complicated, but it's very simple. What it says is the following. Imagine that you want to generate an estimate of the image with degradation S, which S is closer to 0, is a slightly less degraded image, given that you are at time t. Then this MMC estimate, right? This is a posterior mean, the MMC estimate of xs given xt is actually equal to estimating the clean image from time t and then doing this convex combination with these very specific weights. And this is a direct consequence of our initial formulation that we assume this convex combination between the clean and the low quality data. So, okay, we have.
Here, what's the expectation?
The expectation is taken over over the like xt here, right? So over the space of the degradation, right? Right. We have x and y, both are data. So imagine that you are going to compute the expectation in that space.
Which one is a random variable?
Well, xt is assumed fixed here because it's given xt, right? I'm going to estimate the mean of this xs. Xs is the random variable if you want to see that in that way, right? This kind of a posterior mean, right? So if I change xt, I will get a different estimate, right?
So you have a prior on the mean is what it is.
So say that again.
Prior on the mean, you're assuming something.
I'm not assuming anything. Maybe later it will become more clear, right? But this is like for a specific time t and an xt, I can estimate this posterior mean, right? Okay, so let's move a little more. So this means that we can actually estimate an image that is slightly less degraded, right? Given that we have an image at time t, we can estimate an image that is slightly less degraded by applying this formula, right? Which is just substituting S with T minus delta. Which then leads to a iterative procedure. Let's say that we start from Y, and then we can apply this iterative recurrence, right? That will give us something at the end when we reach T equals 0. The key thing is like, we actually don't know this guy. We don't know how to estimate this posterior mean, right? This is like the mean of like the estimate of the clean image given a current degraded image at time t. So what we're going to do is just approximate this using a neural network, right? This neural network will learn to estimate the clean image from time t and the current degraded image at time t. Yes.
What's the x hat here?
Hat here is because we get an estimate and then we plug this estimate here. It's not exactly a valid point because we are using, when you go to a recurrence, you need to start from the previous point, and the previous point is also coming from another previous point, right? The difference, the hat means that exactly that is like an estimation.
I see. So this is already the posterior mean you get from somewhere.
Right. Okay, so let's see why this makes sense. To that,
So this has been related with Twitty's formula.
I'm going to share some details of that. It is related. Yeah, it is related. So let me show an example, on why this makes sense. Let's assume that this is a very simple case. We have 2D data coming from 4 possible modes in these orange points. But what we observe is noisy data, the blue points. And the question is, how can we estimate the noiseless data points? So in this case, we actually know everything perfectly. So we can actually compute in closed form this posterior mean and in the iterative rule. We don't really need to learn anything, right? So this is a toy example. But first, what happens if we directly try to find the estimate that minimizes the reconstruction error, the MMC estimate? Then, if we are here, the MMC estimate is going to be this red point. The red point is the point that minimizes the average reconstruction error. But if you look, okay, it may be a great point a great estimate in the sense that minimizes the average reconstruction error, but it's not a valid point in the sense that it's not laying on one of the valid points that we need that the data distribution is, right? And this is also kind of a regression to the mean problem on this toy example. However, if we apply the iterative procedure by InDI, we actually converge to one of the data points, which is what we want. This point is not going to be the one that minimizes the average reconstruction error, but it's going to be a valid point in the sense that it's a point from our prior distribution.
How do you get the red point?
Red point is just directly computing the MMC estimate, right? Which is the posterior mean starting from Y. Right? And you can do it in this example because you know everything, right? It's analytically, you can compute it. All right. Okay, let's see what happens in practice. We can train a model for doing super solution with exactly the same idea. And you can see here the input, the reference. This is what you get when you do one-step reconstruction, which is directly going to the MMC estimate. And as you take more steps, you start seeing much better details, right? So we can train a model for doing motion deblurring, given per data, blurry, high quality data points, right? And then you the same, right? As we take more steps in the reconstruction, we get results that are closer in terms of perceptual quality to the target reference. An interesting thing is like what happens on this plot, on the second part, which is what we call a perception distortion plot. I'm going to show many of these, so let me explain a little bit what do they do. So we have two things. FID score, which is a kind of a perceptual metric, or meaning the average quality in terms of how the quality of the samples that we generate. The lower, the better. And then we have PSNR, which is a distortion metric. The larger PSNR, less average distortion, right? So each of these points represents applying InDI with different number of reconstruction steps. If we do one step, we're here. We get very high PSNR, but very bad FID, meaning that the perceptual quality is not great. Results are blurry, but the average reconstruction error is pretty good. As we take more steps, we traverse these curves, and we get into the regime where we have high perceptual quality, lower FID, but we're trading off PSNR. I mean, maybe you are already familiar with this perception distortion trade-off. This is a very nice work by Blow and Michaeli that they actually present this in a theoretical framework. They show that there is this trade-off. You cannot actually minimize the two together. And with InDI, actually, by setting the number of steps, we can traverse this compromise.
So if this were denoising, the first step would be very close to the original noisy data, and so I would expect to have a poor at PSNR. Is this noiseless but blurred data? Is that what's happening here?
So this is not the first step. It's actually applying InDI with one step.
Oh, I see.
Right.
Okay.
This is clean but blurry, right? I think that's a great differentiation, right? Yeah. So it's like going through InDI, let me like maybe here, right? But just keeping the first step estimation, like from X1 or Y, estimate the clean image. Nice.
What's the statistical property for the toy example?
What is that?
Can you switch to the
Yes.
What's the statistical property of those four orange dots? Are they like posterior mode or something?
This is the prior. It's exactly this. So you actually you are sampling from the prior.
You can think of it as a mixture of Gaussians with.
Yeah, they are very degenerated Gaussians if you want, right? Yeah, maybe the notation is not clear, right? But yeah, these are like, yeah, very concentrated Gaussians if you.
I actually have a quick question. So you mentioned that this is kind of like a diffusion process, and then you start from a blurry image, you go to a clean image. But I imagine if you have something like some sort of compression artifact, then a convex combination of the blurry and the clean wouldn't represent like an actual image you would get in the real world, because it's like a combination of a compressed and an uncompressed image. Does that have any?
I get your point, but what you're saying is that the intermediate degradations are not going to be physically plausible, but it really doesn't matter, right? Because at the end points, we are in the right place, right? It's not that through the process, we don't require to be like the same with blur and noise, maybe, like depends on the noise. But yeah, that's a good point. So let me go a little deeper on the technical. Well, okay, some metrics, people love metrics, right? Yeah.
Could you go back to the formula that you have recursive? So you see like you're using the network parameterized, sorry, one slide back maybe. You parameterize the from like some xt estimation to 0, right? So which means that this is depends on you can have different xt, right? So
yes,
the final results we're showing here is from the x1 or from like. So what's the final results you got up to here?
The final result is, I'm going to explain the algorithm later, but the idea is you start from 1 and you move to 0, right? So I'm showing input and the end of the iteration.
I see, in one step?
In 1 step, 2 steps, every of these points represents applying the algorithm with different number of steps.
Okay, I see.
Right.
I see.
And this is when you do 1 step, this is when you do 2 steps. If you do 1 step, it's very blurry. Okay. If you do more steps, you get better results.
So the input for your network, like output, the input is also some like time dependent, right?
The input, yes, is the output of the previous stage. Right.
Okay, yeah, I'll look forward to the details.
Okay.
Just wondering, like, if you go more than 30 steps, is the PSNR gonna converge to like around 30 or go even lower?
Say it again.
If you do more than 30 steps, like,
okay,
the PSNR has a lower bound of it, or it's gonna continue going down.
Right. I mean, here you can see that PSNR's like quality starts getting worse. These numerical issues, right? Model training, many other things like make that if you, at certain point, there's no improvement on going more and more, at least with this formulation, right? It's like results will get worse. So I don't know if that was your question. Okay. Good. So let me present a bunch of technical details. So this is the recurrence, right? We have an estimate, compute the clean image, compute this convex combination, and then again repeat. So one thing is like, in order for this guy to be well defined, we need this probability to be everywhere non-zero, right? If not, means that we arrive to a place where we don't have enough signal to know how to estimate the clean image, right? And in this may be like a technicality, but it's not. Actually, this is important in some applications, as I will show, right? So one way to regularize this is by adding just little amount of noise to Y. If we add a little amount of noise to Y, then all the distributions are going to be supported everywhere because it's just smoothing the distributions using a Gaussian kernel, right? And then no matter where we are, we will be able to estimate the clean image, right? So, and this is actually quite important in some of the problems. So in the end, what we do is slightly different. Instead of defining the intermediate degradations in this way, we take our training data, we add a bunch of noise where this epsilon is very little, and then we simulate this data for train our model. So to go into more the details, we need to train a model. Actually, what we're training is kind of a family of models. Each of them specializes on T from 1 to 0, right? So we are going to parameterize that using a neural network, and then we sample per training data, simulate the degradation xt by sorting T in a random, like maybe like a uniform distribution between 0 and 1, so like sampling the noise, generating the xt, and then learning to predict x, right? And we can, for example, try to minimize the L2 reconstruction loss or L1. It really doesn't matter much. And here the parameter epsilon controls the amount of noise that we will add. Then during inference, once we train the model, what we do is very simple. We first start from Y, add very little noise, this is optional, or depends on the application. And then we move from time 1 to 0 by decreasing time steps, get the estimate, generate the convex combination, and repeat, so on till we reach 0. And that's it. We need to fix the step size or the number of steps we want to run. Yes?
Yeah, why there's a need for adding those noise? Because for original diffusion model, they added noise because they want to transform from image distribution
Right.
to noise. But
So-
here, you already have two distribution.
So the thing is like for this, right? In order for this guy to be well-defined, imagine that you're doing super resolution and your Y actually lives in a lower dimensional space, right? Then it's very degenerate, that case. So you're trying to map a distribution that is low dimension into one that is higher dimension. If you add noise, now everything is high dimension, right? You fill in the space. And I'm going to show you some results why this has like strong empirical consequences. I agree that the role of noise, we may need to work a little more to fully understand what's going on. All right, so, okay, in terms of the model, we didn't really innovate much. It's just a unit with big blocks. It's fully convolutional. We remove things that make the model adapted for running images of different sizes, which is, for example, self-attention and group normalization. Because in general, in image restoration, you want to have models that can actually run on different resolutions. So, I mean, please check the paper if you're interested. The details, like each of these blocks is actually look like something like this, where we need also to embed information about in which time step we are, this T that goes between 1 and 0. We do this through these dense connections that get added here. But there is not really innovation here. So, okay, what is the role of noise? Let me show you an interesting example where we're doing super resolution. Super resolution, like clean super resolution, meaning that we just do bicubic unsampling, and then we try to recover a high resolution image. Here you can see 3 different similar distortion perception plots for different amount of added noise. Blue is no adding noise, and then we have orange, which is 0.005. Images are normalized between -1 and 1. So this is very, very, very tiny, a small amount of noise. But actually, if you don't add noise, it really doesn't work. It gets stuck here. Even if I take more steps, I cannot get away from this part of the plot, which is the regression or single shot estimation. But as soon as I add very little noise, pluff, starts working. And I can generate samples that are much better in terms of perceptual quality. So noise is actually playing a big role, at least on super resolution and other tasks like compression artifacts removal. Let me show you a bunch of examples. Right, super resolution. Again, removing compression artifacts. Here you can see that you remove compression artifacts. It's the same model. Here you can see a close-up. One step is very blurry. When you do more steps, you get much more better details. motion deblurring. Okay. This is a nice example because it's very hard to model analytically, which is like removing out of focus blur. But we can capture data that have different depth of field by changing the camera parameters. So then we can train a model. All right, so let me push these ideas a little more and try to see what we can actually do in terms of like generative modeling. Is there any questions so far? Or we're more or less, yeah?
For the last part where you showed the defocus restoration, were there defocus examples in the training set?
No, this is, we have like train set and evaluation, like they're.
Well, I don't mean it's this specific example in the training set. I'm asking if there were examples of defocus.
Yes. Ah, right, yeah. I mean, we need to train a model for a specific use case, which is using defocus pair data, yeah.
So you can handle different image sizes, but a given trained model is for a specific kind of degradation.
For a specific kind of degradation. I mean, yeah.
Why is that? Because the defocus problem is like just deblurring in part of it, right?
Well, yeah, I mean, the thing is like we didn't really train a model that actually handles everything.
Mm-hmm.
I don't think that there is some like hard limitation on doing that. The thing is like you need to have the data, right? Maybe you can simulate compression artifacts on top of this data set and then you get rid of the two, add noise, right? But we haven't really played with that. This is something relevant. Like I think that it's relevant to the practical problem where you do see multiple degradations together.
Can I follow up on that? So you mean like this is task-specific model, right?
It's task-specific
Yeah.
model,
So how
right?
about like denoising with the different ratio, like factor or the different noise scale or different solution scale?
Right. I mean, in what I presented, in the only place where the actual model of your data appears is here, right?
Mhm.
So if you hear your Y has different noise levels, your model will learn to deal with different noise levels. Maybe the performance is suboptimal that if you train a specific model for a specific noise level.
I see.
But it's encoded implicitly here. There is no really notion of degradation. We're just mapping Y into X.
Right. And how do you see like the difference or similarity with like with this kind of line of work with the supervised diffusion model, like the I2SB, which you're trying to find the distribution change along the T to mapping from like one distribution to another, from low resolution to high resolution.
Yeah, I think that it's similar if you want. Like I'm going to show later that this is similar to diffusion models, right? I mean, you already know like what we're doing is, the difference is that here we need pair data and that's it. We don't need an analytical degradation. But it's true that we're not addressing a more challenging problem, which is when you don't have pair data, we just have Y and X, the two distributions, and you need to learn a mapping. I think that as I think discussed this with some of you today, I think that this is an interesting challenge in how to mix things where you have semi-supervised. You have a lot of pair data, but also unpaired data, right? How you create a framework that actually allows you to do that. All right, so let's go back. Okay, so I already mentioned that if we take this to the extreme and say, look, now my input is severely damaged, and I need to generate an image that is compatible to that observation, it may be any image, right? So this is a purely generative task. So one thing we could do is try to learn a mapping. Imagine that we have our high quality images X, and we want to learn a mapping that takes us from noise to high quality images. Well, again, if you directly try to minimize the average reconstruction error, this doesn't make sense, right? The only thing that you can learn is the mean of your data set, right? This is the worst possible generative model, right? And this is kind of the extreme case of regression to the mean, right? You're just learning the mean. However, we can do exactly the same formulation, but instead of starting from a pair Y, we just say, let's Y be noise. And then exactly train the same. And like we generate these intermediate convex combinations and we train a model and apply the same idea. Well, if you do this, then we can actually generate samples. This is actually a generative formulation. And I mean, the results are not state of the art. They are good, but they are not state of the art. But we really didn't change anything for this application. And I mean, for those of you who are familiar, this is very similar to DDPMs, denoising diffusion probabilistic models, right? The main difference is that we are not engineering any degradation. We are just saying we have noise and we're going to map it to a clean image through this, right? The degradation is encoded on the model that we're learning through this intermediate degradation. All right, so I think that right now everybody is familiar with denoising diffusion probabilistic models, but the idea is the following. Let's say that we want to generate images. So the way to go is these models, what they actually do is they define a forward process that is adding noise and noise and noise little by little. Till one point, I only have noise. And then the idea is to reverse this process by denoising little by little. And this is kind of the state of the art on image generation today. And this seems like a kind of similar to what we're doing, but in a very specific application, which is removing noise. So let's say, working. Okay, here it's fine. So let's say that the idea of a denoising diffusion model is to transform noise into a high quality image by repeatedly applying a denoiser. Imagine that now we want to solve other restoration tasks like removing blur. Well, the goal is to train a conditional diffusion model. Like if you want to do a denoising diffusion strategy, we can train a conditional denoiser that actually learns to transform noise into a high quality image, condition on the low quality image. And there are multiple works doing this for example, super resolution. In our formulation, it's slightly different. In the same framework, we can actually learn to generate, if we start from noise, or to improve an image little by little, right? It's more straightforward than always starting from noise. And let me show you a vanilla comparison of a conditional diffusion model and InDI, right? The same type of plot, distortion perception, 1 step, 2 steps, 4 steps, we get into the perception, the higher quality. And in blue, you can see a conditional diffusion model trained for removing compression artifacts with a strong quality, like very low quality factor 15. And these are two different metrics, FID score and LPIPs, that are more correlated to perceptual quality. So the key thing here is that, let's say that we're here in the plot. Well, InDI actually produces better results for a given PSNR in fewer steps, which makes sense, right? Because you are not starting from noise. You are starting from the low quality, which is already an image. So this gives us an advantage over the traditional conditional diffusion model. Any question?
Yeah. Sorry.
So my question is, so the difference of conditional DDPM and InDI is that DDPM, they usually we concat the condition into the into the noisy vector, or we do some other like cross attentioning or some other methods. So but in InDI, you directly using a convex combination of the noisy image and the clean image. Yeah. So do you think is this convex combination contribute to this improvement, or have you, or is it because we can also try to use DDIM inverse to map the low resolution image to the noise and then get back through DDPM? So I'm just curious what contributes this.
Well, but even if you do that, so even if you do that, even if you reverse the image into noise, your sampling will start from noise.
Yeah.
So it will require a lot of steps.
Oh, yeah.
Right? Here, you start from here.
Yeah.
So naturally, the number of steps that you need is fewer, right?
So what you're comparing here as the conditional diffusion model or conditional DDPM is, you mean like during training, the pair data is also used to train it?
Exactly the same model. The only difference is that the input is one image and the input for these two images because it's the noise vector and the low quality input. But the architecture is exactly the same, training is exactly the same.
I see. So how about like the, I'm not sure what's the backbone you're using, but how about the conditional diffusion, like IPSB, not exactly from the noise, but from the low resolution?
Say it again.
So there is also a line of the diffusion model for the acceleration, right? So in order to reduce the sampling step, they not starting from the noise, but they also use a pair data to train that in order to achieve the result, like within several steps.
Yeah. I agree. I mean, this is like comparison to a vanilla. Then there are multiple ways of accelerating these guys or even InDI, right? Which is distillation or other things, right? But I'm here what I'm presenting is like the two formulations without like tricks that you can do to accelerate each of them. And I think that the formulation from the very beginning are different in the sense that this needs to start from noise, right? Then there are hacks that say, oh, you know what? I'm going to fine tune and start from the low quality plus noise. But then what is that formulation? It's different, the formulation, right? It's closer to this formulation, maybe. It's not that clear what you are actually doing if you do that.
Yeah, they're still trying to find the kind of like interpolated contribution at the different time state.
Right.
Yeah, there is also something called the stochastic
interpolants.
Yeah, they're also trying to,
Well, stochastic interpolant is very similar to InDI.
Yeah, that's what I mean. There is still some people trying to find the distribution matching, not from the noise, but from some distribution matching.
So I think that what are we doing with time? Okay. So I think that let me go a little bit and then we. So another interesting thing that we can do is analysis, right? And let's say that we have our iterative rule and we make delta, the step size, go to 0. Then we actually end up having an ODE, right? It's like just applying the definition. You get this so nice, very nice ODE, which actually saying, oh, you know what? You need to evolve your image on the direction given by this residual, which is the current decimate minus decimate of the clean image weighted by t. And this is kind of, we call this a residual flow. And this is useful for doing analysis, but also for exploring other solvers. Actually, if you solve this ODE using Euler method, you get back to the original discretization. But you can do other solvers, and we have done that, and you accelerate even more. And this is related to stochastic interpolants and other works that are out there, rectifying flows. I mean, there are a bunch of papers that are more or less simultaneously. The difference is that here we start from very basic principles, which is, let's try to avoid this regression to the mean. There is not really a probabilistic formulation. So let me show you another thing that is interesting. Like in the case of pure noise, right? Then our ODE is exactly the same as the score matching probabilistic flow, ODE, given by Song. I mean, it's just like writing the probabilistic flow and then replacing the right terms, right? And we get to exactly the same ODE. And the nice thing is like when F, our neural network is actually the MMC estimator, right? This posterior mean, then the denoising score matching formulation is exact and it's given by the 2D formula, right? This is a nice connection because it feels that we are doing something that actually in the physics already was kind of there. The interesting thing is like, we are taking this into a next step, which is using this for generating images now, right? So another thing that we can do is analysis. Like, let's say that we have a very simple prior. Let's assume that we want to do denoising and our signal is given from this prior, which is just a Gaussian distribution. And the noise is also of known variance. Then we can actually try to compute this ODE. And actually, in this toy example, we can get it in the ODE analytically. And one nice thing is that this ODE is actually separable, so it's very easy to solve. So what we're interested is in finding the solution starting from this point at time 0. And we can actually do that. And this is what we get. This is in the estimate for this particular problem. And okay, does this make sense? Well, it makes sense in the sense that if noise is very low, this guy is very small, right? Then you get Y, right? Noise is very small, keep the input. If noise is very large, this guy is very large, then you get the prior. Okay, this makes sense. But more interesting, we can actually compute the map or the MMC estimate. In this case, both agree because everything is symmetric. But look, it's kind of similar, but not the same, right? It has a similar form, but it's not the same. The difference is a square root. So we don't know, I mean, there are many things that we don't know. For example, we don't know where InDI is converging. It's converging to a point that is higher quality, but how can we define that estimate? We don't know. We know that it's not the map estimate. Even if we can say that we are doing map estimates locally, we are not converging to a map estimate, which makes sense. But it has similar properties. Another interesting property that this has is the following. If we take, so here everything is Gaussian, right? I'm not saying that this is going to be general. But since everything is Gaussian, this guy is also Gaussian. So if we find that the first and second moments, then it will be perfectly defined by the first and second moments. And it's easy to see that the first and second moments match to the ones from the prior. So actually means that InDI actually is generating samples from the prior, which is something good for generative model. So these things that we can do that are toy examples, but it allows us to do that because we have this very nice ODE formulation. So,
sorry, what's the PX?
Say that again.
Next page, PX. It's a Gaussian? Or?
The PX is this Gaussian, right? Where we start.
Yeah, I also want to like comment that. Yeah, so in my experience, I tried use Tweedy's formula. If I add like square root on that, sometimes it gives, I think, some better FID images. And I just
look at that. Well, I mean, yeah, I guess that it makes sense. The other thing is like, okay, what happens? So another thing is like, if I add a 1/2 here, I get the square root. Okay. Can we hack that to develop a family of estimators? I don't know. Okay, so let me close this part. So to summarize, so we introduced this framework, InDI, that is really, really motivated by principles, like trying to minimize this regression to the mean. But in the end, we end up with this kind of diffusion method that actually is very related to other ongoing work. And the main difference is that here we don't have like an analytical degradation just per data. And then from there, we learn this family of regressors that actually allow us to recover an image by applying this iterative restoration. And I mean, it's competitive state-of-the-art on several restoration tasks, but it's also a generative framework. So there are a bunch of open questions that we're interested in addressing. Like one is, okay, let's say that you are given 4 steps. What is the best you can do? And this is much more related to current distillation techniques, right? And it may be also very relevant to our ODE formulation, right? Because in the end, what we want to do is like find the endpoint of this solution as fast as possible. Right? So this is interesting work that we want to do. We work in the pixel space, but we can work on the latent space, and maybe results are better there. And one thing that, I mean, some of you asked is like, can we address multiple degradations? Well, right now, everything is encoded in the data, right? Y and X. So if we have data that really represents that, it may be possible. Very challenging problem is out of distribution generalization. Like, we train a model, but then on reality, we see images that have slightly different degradation. How will the model perform there? How to enforce robustness there? This is very challenging, and I think it's one of the main problems with this framework, but all frameworks like generative modeling in general. So, like to finish my talk, I wanted to show you something completely different, which is it's also related to image restoration, but more from the industrial and perspective, which is what we can actually do and what we're actually doing. And in particular, I wanted to show you something that we launched last year that is called Unblur, right? And the idea is that it's a feature that actually removes blur, noise, and compression artifacts from images, right? That runs on the device. This is a very challenging problem because almost every photo is out of distribution, right? People apply this to images coming from multiple devices, photos that have been resized, post-processed, it's very hard to model actually this. So the other interesting thing is like it got advertised in the Super Bowl. So let me show you because it's kind of cool. So yeah.
Oh, now it's giving.
Oh, cool. That's his famous.
Touchdown! Awesome.
Totally awesome.
Okay. Okay, bunch more examples. So here you can see that there are compression artifacts and some noise. For example, this is Peyman Milanfar, for those of you who don't know him. And this is me. So with that, let me thanks again for attending this talk. And I mean, if you have questions, I'm happy to answer if we have time.
Thanks for great talk. Any questions from audience?
Let's start like from here to there.
So I'm wondering, like, if you wanted to apply some sort of constraint to this method, like here you're generating images, but like, let's say you wanted to generate some other kind of system, like, I don't know, if you have like some physical system and you're representing objects as like points and they should have certain physical constraints on them. Like, are there ways that you know of that would be able to work with this method?
Right.
Sort of thing, or?
Yeah, that's a good point. It's not as straightforward, right? Because here we're learning everything from Y and X, this distribution, right? So either you do that during the learning or you do it during the sampling, like maybe by back projecting and enforcing the constraints there. But if not, it's not that obvious how to do that. I think this is like a common problem from many diffusion strategies also.
Right, yeah, I was just wondering if you had, if there's anything particular about your method that made it easier to do that or not.
Well, one thing that you could try to do is try to force like whatever. So let me go back. So I start with this convex combination, right? If there's a way for you to define intermediate degradations that are plausible reconstructions, then it may be better, right? If at each point you are seeing something that is satisfy your constraints, maybe your model learns that, right? More question, yeah.
I just had a comment. There's a paper called cold diffusion. I don't know.
Cold diffusion, yeah.
And I think the main takeaway in that paper is that you don't necessarily need to start from noise to generate another image, right? So if the only benefit, well, not the only, but if a benefit of InDI is that you don't need to necessarily start from noise.
Right.
Right? Is there a way you can adopt the cold diffusion framework?
Look, yeah. two things. One is like in the paper we compared to cold diffusion, sampler is much worse.
Okay.
And the other thing is like, I don't agree. I think that we need noise. I think that and even here, right? I show you here that if you don't add noise, where was it?
Well, I just meant like starting from pure noise, like.
Pure noise, right? In cold diffusion, they claim that they don't need noise.
If they don't need Gaussian model, you can add any noise.
Any noise, but they don't discuss, like, they do try to do super resolution without adding any noise. Right? And I personally think, and my experience, that you need noise because of this. This is not just a technical thing. Where was it? This is actually important. You cannot, I mean, for me, it goes back to optimal transport. If you are trying to transport a distribution to another one, and they are living in different dimensions, it's not that easy, right? Imagine in the limit is like, imagine we can take super resolution to the limit, and it's just starting from 1 pixel value and generating a new image. I mean, it may be super hard to do that, right? Even if I can I can say that there is a continuum possibilities there, maybe there is a way to do this mapping, but it's very hard because they live in very different dimensional space. And when you add noise, you are back again to things that are living on the same dimensional space.
Yeah, question is similar to his question. Yeah, in diffusion model, you generate the image from noise, right?
Right.
In your model, you generate the image must from some low quality image, right?
Right.
You cannot generate image from random noise.
Yeah. I show that actually. Like this is, I mean, we can actually apply the same framework.
Conditional.
Right here. To start from noise and generate images.
Yeah, but when you train your model, you're from a low quality image. Right?
No. I mean, we
can train from auto train from noise. So,
I need to train a model for a specific application. If I train a model to start from noise, I will generate the images.
I see.
Yeah, that's maybe the, yeah.
Yeah, can I still ask some question about the toy 4 dot?
Yes, sure.
So like yeah, MMSE estimate will converge to one of the 4 dots as asymptotically as number of sample size converge to infinite. Ultimately, MMSE estimate will converge to one of 4 dots.
Not really. I mean, when you say MMC estimate, what are you thinking exactly?
I'm thinking about
because if you start always from the same point, the MMC estimate is for where you start, right? It's not the MMC estimate of the underlying distribution. I'm not sure what you're referring to.
Also, like your prior is like for delta function,
right?
And for like the first select one of the delta, and then add Gaussian noise.
No.
Or not.
Yeah, it's the same, right? This is the underlying distribution of my observed data is this, which is, if you want the convolution of this with noise, with the Gaussian kernel, that's my data.
Yeah, so like the X, like for different.
No, that's a Y. The Y is the blue.
Yeah, to generate Y, you need an X, right?
Right.
So for different generation, for different draw, X can be different. X can be.
Yeah, exactly. I actually, when I observe Y, I don't know what is the underlying mode. You observe just one blue point. It may have come from this or from this. You don't really know, right?
Yeah.
And
but for every Y can only be generated from one of the 4 dots.
True.
And like fix that X generate lots of realization of random Gaussian noise. Then the MMSE will converge to one of the.
If I use all the observations, given that they are coming from one of the modes, right? That is what you're saying. But why is that something that you would like to? I mean, how would you do that in practice? Yeah, I'm not sure I follow.
Yeah, or just off. Yeah.
Okay, okay.
Yes, can I just continue my previous question? Like what contributes to the performance gain? Because I look at the performance compared to the conditional DDPM, it looks like it's much better. Yeah, and so my understanding is these some variants of 3D's formula it's leads to a better estimation of the prior model, or because in conditional we just concat the conditioning information into the input, and maybe it is not the most efficient way.
Well, I think that
What contributes to the gain?
two things. One is like, if you look at the endpoints, they are going very similar, right?
Yeah, but
So it seems that it's just a matter of how fast you get there.
yeah, but I'm thinking about if DDPM is similar in endpoint performance, the curve should be, they should have the same curve, but in a different
The problem is that DDPMs, what is the shape of this curve? Because for DDPMs, it's not obvious how to sample using different number of steps. You need to adjust a lot of hyperparameters, right? So actually this curve is like a merge of multiple curves.
Okay.
Because what I try to do is like, let's say that I want to do 100 steps. I did a hyperparameter search to find what is the best for 100, right?
Yeah.
It's less clear how to do this, right? Yeah.
Yeah, that makes sense. And second question is, so in the pixel space degradation, so it's usually, for example, applying blur kernel or some adding noise, but in the latent space, so first all the image will be mapped by an autoencoder. So degradation might be more complicated. And what do you think about this direction? Do we still use the convex combination or use some other technique?
Yeah, there's nothing saying that you need to use a convex combination, and maybe that leads to better results. Maybe the combination is something else. Latent space, I've been experimenting. It works with the same convex combination, right? It really doesn't matter. You're starting from the latent code of low quality and going to the latent code of high quality. But maybe that's not the optimal way. I agree with you in that regard.
Thank you.
Sure.
Then now, how do you decide like what's the necessary steps, how many steps you need to use for different tasks?
Right. Yeah. I mean, that's in the paper. I think that for example, for super resolution, typically we need more steps than for motion deblurring, but this is also really dependent on the data that we have. Like, for example, one thing that happens is that the motion deblurring data set that we use is not really high quality, which means that like you can really create like high quality results there. While in super resolution, if you have like a super high quality data set, you can do better and will require more steps. So, but I would say between something between 10, 15, and 200, right? Something like that, without any acceleration.
I see. That is the table you're showing.
Yeah.
You might have answered this question. Did you use the same amount of data to train both the denoiser for InDI and the conditional?
Yeah, it's exactly the same.
That's exactly the same.
It's just, I mean, if you think it's not that different, right? You need to, I mean, DDPMs, you make condition on the noise level, but it's the same type of architecture, right? You just condition on, and then the only difference is that the first layer has more channels to use the concatenated additional input that the conditional DDPM needs. Oh, any more? I mean, if you have questions later, feel free to contact me and happy to follow up from there.
This might be like a very like minor technical question, but you said you use swish functions in your denoiser.
Swish.
Swish.
Swish, yes.
Does the diffusion model use those, or does it use ReLU? Because my understanding is that it uses like ReLU typically.
I mean, we use that because previous work was using that. I mean, people have been moving from Swish to other things. Like, I don't think it's really. I mean, it's not what we didn't really analyze that. That's my honest. Yeah.
I just have a small comment that like maybe I think one like important thing to make it work better, maybe it's because like the way like it's a linear transform from X to Y. Because recently in the stable diffusion V3 paper, they also use this special scheduling. They name it as the rectified flow. And they have experiment to show it's better than the like what DDPM do. So maybe I think that's also
It's actually one of it's here that Liu. This rectified flow is similar, right? I mean, if I go to the mathematics, it's maybe similar. The main difference is like how we got there, I think. But yeah, I think so. I mean, this has been known as stochastic interpolants, like bridge methods, rectify flow. I think all of them are going into these directions. Cool. All right.
Thank you.
Thank you.
Hi, may I ask, how long does it take to generate an image?
So you have, let me.
Extend resample to line inverse problems. Yeah.